We're looking at an Exam 4 review here, and Exam 4 covers sections 4.1 to 4.3, 5.1 to 5.4, and 6.1 to 6.3. Now hopefully you've spent some time working through these problems before you're looking at this video, giving yourself a chance to figure out how to do them on your own, and that now you're ready to see how to do those problems and make sure that you got the right answers. Okay, so let's start with question number 1. One game at a carnival involves tossing dimes onto stationary plates. The probability of a player landing a dime on a plate on any toss is 0.2. What is the probability that the player's first success will be on the 8th attempt? So this is a type of probability problem. The question is what type? We're looking for first success, so that means that this is geometric. So in the geometric probability formula, probability of first success on the 8th attempt is given by 0.8 to the 7th power times 0.2. Because the way that geometric works is that if you're looking for first success on a particular attempt, you have one less than that many attempts that you fail on. So we do the probability of failure to the 7th power, and then on the 8th attempt you succeed, so that's the 0.2. When we multiply that out, we get 0.04194304. And if we rounded that to 4 decimal places, we get 0.0419. Let's take a look at question number 2. The average number of hurricanes that make landfall in the United States in a calendar year is 3. What is the probability that there will be 5 hurricanes that make landfall this year? Well, what type of probability is this? Because again, we're looking at some kind of probability. We're looking for a certain number of occurrences within a given frame of time. That makes this Poisson. So the Poisson probability formula is the probability of x occurrences is given by mu to the x, e to the negative mu, over x factorial. So we need to know mu and x. Mu is 3, x is 5. So the probability of 5 hurricanes is 3 to the 5th, e to the negative 3rd, over 5 factorial, which is given by 0.1008188,134, rounded to 4 decimals, is 0.1008. Question 3. Consider this probability distribution. So we have x values that go 1, 2, 3, 4, 5, and 6, and their associated probabilities. In this problem, we want to find the mean, the variance, and the standard deviation. So we have formulas to do all of those things. We're going to start with the mean. I'm going to make a slightly expanded table here that includes x times the probability of x. So for each one of these x's, we're going to multiply it times its probability. 1 times 0.14 is 0.14. 2 times 0.27 is 0.54. 3 times 0.41 is 1.23, and so on. So we get all 6 of these values by multiplying. Once we have those 6 values, we need to add up the x times p of x's, because our formula for the mean is mu equals the sum of each x times its probability. So that's going to be 0.14 plus 0.54 plus 1.23 plus 0.36 plus 0.30 plus 0.18. When you add those together, you get 2.75. So that's your mean. Next, we find the variance. To find the variance, we're going to build a table. And we're going to use the easier version of the formula. If you remember from your notes, there were 2 different formulas to find the variance, and one required a lot less work with far less complicated values. So we're going to use that formula. So we're going to take the x's and their probabilities, and we're going to expand the table to include a column for x squared, and then another column for x squared times the probability. So for the x squareds, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and 6 squared is 36. Then we multiply those x squareds times the probability. So 1 times 0.14 is 0.14. 4 times 0.27 is 1.08. 9 times 0.41 is 3.69. 16 times 0.09 is 1.44. 0.06 times 25 is 1.50. And 36 times 0.03 is 1.08. According to the simpler version of the formula, we're going to take those x squared p of x values and add them up. So that's the 0.14, the 1.08, the 3.69, and so on. And when we add those up, we get 8.93. We also need the value of mu squared. So mu squared, remember mu was 2.75, so that's going to be 2.75 squared. And 2.75 squared is 7.5625. Our formula for the variance is that the variance is equal to the sum of the x squared times p of x's minus mu squared. So it's 8.93 minus 7.5625, which gives us a variance of 1.3675. So now we found the mean, 2.75, we found the variance, 1.3675. To find the standard deviation, remember, we take the square root of the variance. So the square root of 1.3675 gives us approximately 1.1694. So our mean was 2.75, our variance was 1.3675, and our standard deviation was 1.1694. Question number 4. One of every 5 items placed in the city's recycling receptacles is not a recyclable item and must be sorted into a different category. A recycling receptacle is chosen at random. It contains 6 items. What is the probability that exactly 2 items will need to be resorted? So this is a binomial problem, because either an item needs to be reclassified or it doesn't. So there's 2 possible outcomes there. So with our binomial, we need to know certain values. The value of n is 6. The value of p, because it says 1 out of every 5 items, is 0.2. The value of q, which is 1 minus p, is 0.8. And the x value is how many items need to be reclassified. In this case, we're asking about 2 items being reclassified. The binomial probability formula is ncx, p to the x, q to the n minus x. So if we take that formula and we begin to insert these values, remember that the n is 6 and the x is 2, so we get 6c2 times 0.2 to the second times 0.8 to the 6 minus second. Simplifying, 6c2 is equal to 15, and then 6 minus 2 is 4, so we get 15 times 0.2 to the second times 0.8 to the fourth. And if we multiply that out, we get 0.245760, rounded to 4 decimal places, is 0.2458. Question number 5. The probability that animal control receives a stray dog report on any given day is 0.31. For a given 30-day period, find the mean, variance, and standard deviation for the number of days with stray dogs reported. So this doesn't seem like there's enough information given, but there really is, because it's a binomial. And in a binomial, we know how to find the mean, variance, and standard deviation with some very straightforward formulas. Since it's binomial, we'll get n equal to 30 because it's a 30-day period. The p is 0.31, and the q is 1 minus 0.31, which is 0.69. The way I know that this is binomial is because they either receive a stray dog complaint or they don't. There's 2 different possibilities there. So, in a binomial situation, the mean is found by doing n times p. So n times p would be 30 times 0.31, which is 9.3. So we have our mean. The variance is found by doing n times p times q. So it's 30 times 0.31 times 0.69. And 30 times 0.31 times 0.69 is 6.417. And of course, when we're finding our standard deviation, we're taking the square root of the variance. And the square root of 6.417 gives us 2.53317,982, rounded to 4 decimals, is 2.5332. So we have our mean, variance, and standard deviation. Question number 6. A local raffle has 3 top prizes, 10,000, 5,000, and 2,000, where there were 10,000 tickets sold for $5 each. You buy 1 ticket. What is the expected value of your gain? Well, in this type of problem, gain is a generic term, and it's used whether you come out ahead or behind. Everything is relative to the gain. So, if you buy a ticket and win, you have to ask yourself a question. What is your gain? If you won the $10,000, your gain is not $10,000 because there was a cost associated with playing. You had to buy the ticket. So you have to subtract the ticket cost from the prize. If you won the $10,000 prize, your actual gain would only be $9,995 because of the $5 ticket cost. So we look at these prizes and we figure out all the different potential gains. We'll build a table. The X values will be our possible gains. So we could either, if we won the $10,000 prize, gain $9,995. If we win the $5,000 prize, our gain is $49.95. If we win the $2,000 prize, our gain is $19.95. And if we lost, if we didn't win any of the prizes, then our gain is -$5, because for us, negative gains are considered losses. So we would just lose $5. The probability that you have the winning ticket is 1 out of 10,000 for any one of the winners, because there are 10,000 tickets sold, and one of those 10,000 will win each of those prizes. That means there's 3 winners total. So if there's 3 total winners, that means there's 9,997 losses. So the probability that you get a loss is 9,997 divided by 10,000. When we're finding expected value, that's just a mean. So we're going to multiply our gains times our probabilities. 99.95 times 1 over 10,000 is 99.95 over 10,000. 49.95 times 1 over 10,000 is 49.95 over 10,000. 1995 times 1 over 10,000 is 1995 over 10,000. And -5 times 99.97 over 10,000 is -49,985 over 10,000. We add all these values together to get our mean. So when we add all these up, we get -3.30, and that means that the average loss per ticket is $3.30. Question number 7. A random variable x is normally distributed with mu equals 350 and sigma equals 44. Find the indicated probabilities. So we want to find the probability that x is less than 280.48, and then we want to find the probability that x falls between 317 and 405. So for part A, we're looking for the area to the left of 280.48 on the normal curve, because less than probabilities correspond to areas on the left. No matter whether we're looking for area on the left, area on the right, or area between, we still need to find a z-score for the x value that we're given. So we'll look for the x value of 280.48 and try to find its z-score. Z equals x minus mu over sigma. So our x here is going to be 280.48, mu is 350, and sigma is 44. When we do our subtraction, 280.48 minus 350 is negative 69.52 over 44, which gives us negative 1.58. Once we have our z-score, we can go to the table of values. So we look at the standard normal distribution table. I've cut out part of it that we'll need to locate that value. So we look up negative 1.58 and we find 0.0571. That's our table value. Because we're doing area to the left, When we do that, area to the left, the table value is the area. So our area here is 0.0571, and remember that area corresponds to probability. So the probability that x is less than 280.48 is really the probability that the z-score is less than negative 1.58, which corresponds to this area of 0.0571. That's part A. In part B, we're trying to find the probability that the x value falls between 317 and 405. So that corresponds to an area in between these two z-score values. So we would have to find the z-score for 317 and the z-score for 405. I always start with my larger value, so we'll find the z-score for 405. It's 405 minus 350 over 44, which is 55 over 44, which is 1.25. We also need the z-score for 317. So we're using the same z-score formula, but now it's 317 minus 350 over 44, which is negative 33 over 44, which is negative 0.75. So now we've got our two z-scores, we can go to the standard normal distribution tables. We'll start with the positive version of the table to find z equals 1.25. So for 1.25, we get a value of 0.8944. To do the other z-score, which is negative 0.75, we need the negative side of the table. So let's switch to the negative side of the table. And we're going to look up the negative 0.75, which gives me a 0.2266 value from the table. Now, when we're finding area that's trapped between two z-scores, it's always the right-hand table value minus the left-hand table value. So this probability that x falls between 317 and 405 is given by 0.8944 minus 0.2266, which is going to be 0.6678. And that's your answer for part B. Question number 8. The average amount of money spent on a dinner in Fresno is $13, with a standard deviation of $4. You randomly select 100 diners. What is the probability that the average amount the 100 diners spent on dinner was between 1180 and 1360? This is a central limit problem because we're not asking about a single diner, we're asking about a group of diners and their average dinner cost. The central limit theorem here applies because the population is normally distributed and sigma is known. So, we need our values for the central limit theorem. That would be mu of x bar and sigma of x bar. Mu of x bar is 13. Sigma of x bar, which is sigma divided by the square root of n, is 4 divided by the square root of 100, which is 4 over 10, and that's 0.40. So when we find z-scores, we're going to use the central limit theorem version of the z-score formula that says z is equal to x bar minus mu of x bar over sigma of x bar. So the x bar value we're using here for the first one is 1360 minus the mu of x bar, which is 13, over 0.40. That's 0.60 over 0.40, which is 1.50. So our first z-score is 1.50. For the x bar value of 1180, we still have the same z-score formula. Z equals x bar minus mu of x bar over sigma of x bar. Now it's 1180 minus 13 over 0.40, which is negative 1.20 over 0.40, which is negative 3.00. So now that we've got those z-scores, we're going to look them up on the standard normal table. Okay, so when z is 150, I need the positive side of the standard normal table. I search for my 1.50 value, and 1.50 has a table value of 0.9332. The other z-score was negative 3.00. That means we need the negative side of the standard normal table. And when I look up negative 3.00, I get 0.0014. And because we're looking for the probability that the average value of the dinner falls between these two, area in the middle is found by taking the larger table value minus the smaller table value. So the probability that the value falls here is given by 0.9332 minus 0.0014, which is 0.9318. That's your answer to question 8. Question number 9. Find a confidence interval for mu if x bar is 93.8, sigma is equal to 5.2, n is equal to 100, and c is 0.99. So you can remember from 6.1 and 6.2, when we're finding confidence intervals for the mean, there's a couple slightly different ways depending on whether we know sigma or not. If we know sigma, then we use the error formula that involves z-scores. If we know s, we use the formula that involves t-scores. So here we're given a sigma value, and since we're given sigma, we're going to use the z-score version of the formula. First thing we need to do is find the margin of error. To find the margin of error, we have to have the correct z-score. With a confidence level of 0.99, the z-score is 2.575. So the error is given by zc times sigma of x bar, which is 2.575 times 5.2 over 100, because the error formula is zc times sigma over the square root of n. When we simplify the fraction, we get 0.52, so it's 2.575 times 0.52, which gives us an error of 1.339. So what do we do with that error? Well, to find the confidence interval, we take the mean and we subtract the error. We take the mean and we add the error. So our confidence intervals are of the form x bar minus error, x bar plus error. So the x bar here was 93.8, so it's 93.8 minus 1.339, 93.8 plus 1.339, which simplifies for a 99% confidence interval to 92.461 and 95.139. That's your answer for question number 9. Question number 10. Find a confidence interval for mu if x bar is 93.8, s is 5.2, n is 16, and c is 0.99. So this looks very similar to question number 9, but now we don't know sigma, we know s. So if we don't know sigma, we have to use the t-score version of the error formula. So how do we start that? Well, the first thing we need to know is what are the degrees of freedom. So degrees of freedom are given by n minus 1, and in this case it's 16, so it's 16 minus 1. 16 minus 1 is 15. Once we have the degrees of freedom equal to 15 and the confidence level of 0.99, we turn to the t-distribution. We find where the row for the degrees of freedom intersects with the column for the level of confidence, and if we look up 15 degrees of freedom and 99% confidence level, we get a TC value of 2.947. Once we have that, we can find the error. So for C equals 0.99, we just found that TC was 2.947. The error is given by TC times S over the square root of n, which is 2.947 times 5.2 over the square root of 16. So that's 2.947 times 1.3. And when we multiply that out, we get 3.8311. Once we have our error, we find the confidence interval by subtracting the error from the sample mean and adding the error to the sample mean. So that's x bar minus e and x bar plus e. X bar is 93.8, so we do 93.8 minus 3.8311 and 93.8 plus 3.8311. When we simplify that, we get a 99% confidence interval of 89.9689 and 97.6311. If you were to compare this value to the value in problem 9, you would see that this is a wider interval, and in general, if you have all the other values the same, except for your n, and you're finding a t distribution versus a z distribution error, the z distribution error will be smaller. Question number 11. From a random sample of 36 days in a recent year, the closing stock prices for Hasbro stock had a mean of $24.19 and a standard deviation of $1.08. Construct a 95% confidence interval for the population mean. In this case, we're finding another confidence interval, and we need to know what we have. Do we have sigma or do we have S? So it says in a recent year, the closing stock prices for Hasbro stock had a mean 24.19 and a standard deviation of 108. So that's the standard deviation for the whole year. That makes it a population standard deviation. So we're going to use the z-score version of the error formula. When c is 0.95, zc is 1.96. We had that from a table of values given to you in section 6.1. Once we know the zc value, we find the error. Error is zc times sigma of x bar, which is zc times sigma over the square root of n. So this is going to be 1.96 times 1.08 over the square root of 36, which is 1.96 times 0.18, which is 0.3528. Once we have the error, we find the standard deviation by subtracting the error from the sample mean and adding the error to the sample mean. So once we have the error, we subtract the error from the sample mean and we add the error to the sample mean. So we're going to take 24.19 minus 0.3528, 24.19 plus 0.3528, which gives us a 95% confidence interval of 23.8372 and 24.5428. Now understand, this is not how we're going to leave the answer. So even though we had a problem that said round to 4 decimals at the beginning of the test review, that was the instructions, this question is not going to be a 4 decimal question. And the reason for that is that this deals with money. And in general, when we're dealing with money, we always round to 2 decimal places. So this would be in the proper form 2384 to 2454. That would be our confidence interval here, because this is dollars and cents. So whenever you're dealing with dollars and cents in confidence intervals, you're going to round to 2 decimal places. Question number 12. In a random sample of 14 computers, the average repair cost was $130 and their standard deviation was $12. Assuming that the repair costs are normally distributed, construct a 90% confidence interval for the population mean. Okay, so here we do not have the population standard deviation. It says the average repair cost for these 14 computers was $130 and their standard deviation was $12. Not the standard deviation for all computers, but for these 14. So since we don't have the standard deviation of the population, we have to use the t-score version of the error formula, and that requires us to first find the degrees of freedom. So degrees of freedom are n minus 1, which is 14 minus 1, which would be 13. Once we know the degrees of freedom, we can turn to the t-distribution. We're going to find where the row for 13 degrees of freedom intersects with the column for 90% confidence. And so when we find that on the table, we get a t-score value, Tc, equals 1.771. Once we've got the t-score value, we can find the error. Error is given by TC times S over the square root of n. The TC is 1.771 times 12 over the square root of 14. When we multiply that out, we get this long decimal, 5.679835913. Rounded to 2 places, because again this is a money problem, is 5.68. Once we have our error, we can move towards the confidence interval by taking the sample mean and subtracting the error, and taking the sample mean and adding the error. So we've got x bar minus the error, x bar plus the error, which gives us 130 minus 5.68, 130 plus 5.68. So the 90% confidence interval here is $124.32 to $135.68. Question number 13. The weight of full-grown German Shepherds is normally distributed. A sample of 80 full-grown German Shepherds is measured, and it is found that their average weight is 101 pounds, with a standard deviation of 9.9 pounds. What is the minimum sample size needed if you desire a margin of error of 2 pounds with a 95% level of confidence? So, when we're dealing with minimum sample size, we have a formula. N equals ZC times sigma over E, that fraction squared. When we have a 95% level of confidence, our ZC value is 1.96. So this is 1.96 times 9.9 over 2, that quantity squared. We multiply our numerator, and we get 19.404 over 2 squared. 19.404 over 2 is 9.702, and we're squaring that. That comes out to 94.128804. And with minimum sample size, we always round up. Whether the rules of rounding would say we do or don't, we always round up to the next highest whole number. So in this case, the minimum sample size is 95. Question number 14. In a survey of 1,400 U.S. households, 924 indicated that there were at least 2 children in the household. Construct the 99% confidence interval for p hat. So, we have to find the values of p hat and q hat. P hat is 924 over 1,400. Simplifying that to a decimal, it turns out to be 0.66. Q hat is always 1 minus p hat, so q hat is going to be 1 minus 0.66, which is 0.34. So those are our values for p hat and q hat. Once we have those values, we can turn to the error formula. So we know that when the confidence level is 0.99, the z-score value is 2.575, and we just found our p hat and q hat values. P hat is 0.66 and q hat is 0.34. So we turn to our formula. Error is zc times the square root of p hat q hat over n. This is a population proportion, so it has a different error formula than the mean does. This is going to be 2.575 times 0.66 times 0.34 over 1,400. When we simplify that, we get 0.0326005286. Rounding to 4 places is 0.0326. So now that we've got our margin of error, we find the confidence interval by doing p hat minus the error and p hat plus the error. So p hat was 0.66, so it's going to be 0.66 minus 0.0326 and 0.66 plus 0.0326, which gives us a confidence interval of 0.6274 to 0.6926, or if we wrote it in percent form, 62.74% to 69.26%. Question number 15. You're a travel agent and wish to estimate within 90% confidence the proportion of vacationers who use an online service or the internet to make reservations for lodging. Your estimate must be accurate to within 4% of the population proportion. Find the minimum sample size necessary if a previous study indicated that 82% of vacationers said they used an online service or the internet to make their lodging reservations. the minimum sample size formula for population proportions is different than the minimum sample size formula we use when we're finding the minimum sample size for the mean. Our minimum sample size formula here is n equals p hat q hat times zc over e squared. If you don't have an estimate for p hat and q hat, you use 0.5 for each one, but here we do have an estimate. The previous study indicated that 82% of vacationers said they used an online service, so our p hat would be 0.82, and our q hat would be 0.18 because q hat is 1 minus p hat. So we get 0.82 times 0.18. When we're doing a 90% level of confidence, the z-score value is 1.645, and the error, it said was 4%, we write that as a decimal, 0.04. We divide the value in the parentheses, and that's 41.125, so we get 0.82 times 0.18 times 41.125 squared. We're only squaring the 41.125. So let's go ahead and square that first. That squared is 1691.265625, still being multiplied by the 0.82 and the 0.18. And when we multiply all three of those numbers together, we get 249.6308063. And we always round up when we're finding minimum sample size, whether it's minimum sample size for a mean or for a population proportion or anything else. Minimum sample size we always round up to 250 in this case. And that's your answer. So that brings us to an end of this Exam 4 review. Study hard. If you have any questions, send me an email. There will be exactly as many questions on the exam as there are on this review. And good luck.